Next, I'm going to draw out some ionic compounds. To contrast with what I did before, a covalent compound is made up of only nonmetals, which means that whatever electron movement there is between the atoms of that molecule, it's going to be relatively minimal compared to the electron movement in an ionic compound. Because in all of these pairs, potassium and oxygen, aluminum and sulfur, lithium and hydroxide, the metal of that pair is going to be so much less electronegative than the nonmetal, and so it's going to so easily give up its electron and completely transfer it over to the nonmetal. And so I'll draw that out. I'll do a relatively easy one first just to show you the steps of drawing, and then I'll go to a relatively complicated one, which is the beryllium and the chlorate, to show you how that works whenever there's a polyatomic ion. So I'd recommend drawing the Lewis dot structures first, and whenever you've got potassium, that is relatively easy because the Lewis dot structure is just one electron. It has one valence electron. The oxygen over here is going to be a little bit more complicated because it has the 6 valence electrons, but still nothing too bad. So I'm sort of spacing those extra valence electrons out evenly. Doesn't really matter where you put them as long as you do them evenly on all of the outside. Now at this point you can put electronegativities on here. I'm going to, just so that we can so easily see why the electrons are transferring from the potassium to the oxygen. Oxygen has an electronegativity of 3.5 and potassium has an electronegativity of 0.8. And I'm just looking at the periodic table in order to see that. Right now, it's really easy. Potassium wants to give up its electron, oxygen wants to grab electrons, and so I'm going to use an arrow to show that the electron is moving from the potassium to the oxygen. Any electron that has moved over, I'm going to indicate with an X to show that now the electron is no longer at the potassium, it's actually with the oxygen. So now this potassium has completely satisfied its octet because it's gotten rid of its 1 valence electron and revealed, which we don't show by the way, the valence shell underneath. But the oxygen is not quite content because it still has 1 more electron that it needs to grab. Our only options are potassium and oxygen, and so we just draw another potassium and draw its valence electron and show it moving over, crossing it off from where it was and showing that it has moved over to the oxygen. Once that happened, the transfer is complete, and so we can indicate that oxygen has a charge of 2- and that potassium has a charge of 1+. And as a result, the potassium and the oxygen are attracted to each other. And so we can show that in a kind of a grid. So we are going to draw those ions in brackets. This is the official way of doing this. You have 2 potassiums, each that have a 1+ charge, plus 1 oxygen, each that, well, it has a 2- charge. And I'm going to draw the valence electrons around the oxygen to show that that transfer has occurred. And once I've drawn this out, I'm going to write it as a chemical formula, which is to say that I have 2 potassiums and 1 oxygen. This is the bracket and charge form, and this is the chemical formula. And that's just saying that in potassium oxide, which is this particular chemical, there's always a ratio of 2 potassiums to 1 oxygen. The 1 oxygen takes 2 electrons, and the 2 potassiums each give up 1 electron.